Hello, everyone, and welcome to today's presentation on GSA. As you can see, the topic of today's webinar is GSA getting it right. And what we mean by that is that GSA is a powerful program, and this means that you need to make you need to make sure that you are asking the right questions in the software to get the right answers. So what we are trying to do today is that we will try to look at some typical modeling errors and show you how you can fix them in the future. So today's team, we have Peter Debney, our application specialist and chartered engineer at Oasys, and myself, I'm business development manager working for Oasys team. As you may have noticed, we have recently released GSA 8.7, and there are a number of new features and improvements in the software, including new steel codes, steel design codes, reinforced concrete slab design codes. Most importantly, nonlinear shell elements, some improvements in seismic aspects, and also faster processing time. So you can find the list of new development features on our website. So if you go to GSA and then click on what's new, you can see a slide covering all those aspects in details. Okay, so what I want to do now is to ask my colleague Peter Debney to continue the presentation from this point, and we will answer your questions at the end. Thank you. Over to you, Peter.
Thank you very much, Nick. Now, what this webinar is about, I've been working for Oasys now over 10 years, helping engineers like yourself find mistakes in your models where things have been going wrong, and I've also been making my own mistakes for nearly 30 years now in engineering analysis, which is a little bit scary. And so the idea of this webinar is I want to share with you where I go first when I receive a problem model, and where to look. Now, thankfully, structural collapses are very rare, but unfortunately when they do happen, people do get hurt. Well, we're walking on a tightrope of structural efficiency with minimum materials and cost, but still ensuring that nothing goes wrong, nothing will fail. Most of the images you'll find in this presentation are light-hearted, but if you do a picture search in Google for building collapse, unfortunately you won't see very many happy images, and it's quite a sad experience. So let's see what we can do to avoid it happening first. I will look in detail at one, the Schleppner offshore platform, which, as far as I know, nobody was hurt in this one, and certainly is a good example to look at because finite element analysis was a major contributor to this this disaster. Now, Schleppner was a gravity-based platform in the North Sea, with principle is all these. There are 24 concrete cells in the base, which initially are filled with air, so that the base will float, and they tow it out in the North Sea, fill them with seawater, it sinks to the bottom, and they can then replace the seawater with oil and for storage and so on. Unfortunately, it went wrong. Now, the cells there, you can see the cell in the middle must be filled with air initially, or seawater and oil, and the triangular areas between were open to the sea, which means that at full load they should be designed for a depth of 82 meters head of water. Fair load. But the structure collapsed, broke up during the towing operation at a mere 65 meters head of water, which is way below the design requirements. Cost $700 million to replace in mid 1990s prices, and subsequent investigation found that the FE meshing was quite inadequate, and that there's a section of the model on the right hand side. The lack of detail in the mesh meant the shear stresses, for example, were underestimated by nearly 50%. So the reinforcement design was well under capacity as well, but single errors don't always cause disasters, but unfortunately the detailing on the Schleppner was also flawed as well. And rather than having proper bars where the shear bars went all the way across, they just had these T-headed bars sections, and they failed horribly. So bad detailing and bad analysis combined together to form a design which fails. Hopefully we can help you avoid at least analysis problems. So what can go wrong in analysis? Most errors in a GSA model are usually come about because GSA is doing what it was told rather than doing what you wanted it to do. Sometimes the errors are subtle, sometimes not so. Sometimes modeling errors, sometimes data entry errors, very rarely software errors. We have a lot of testing goes into software to ensure that doesn't happen. It's still a risk. No software is perfect, and as always, as engineers, you need to know what answers you're looking for in the analysis. So when you get answers out, you can tell whether they're good or not. But the basic principle of all these is put rubbish into the model, you'll get rubbish out. So let's look at places where the model can go wrong and how to fix them. First concept to note is FE is a matrix analysis. Now the matrix is hidden underneath the bonnet, but it's useful to know, at least have an idea of what's going on in there. Let's take this simple arrangement of bars. If the bottom node moves, then all the bars will elongate, and we can work out the elongation of each of the bars based on the vertical and horizontal movements. And when we have the elongation of the bars, we can then work out the forces and the stresses in the bars, and so on. And note, of course, that the forces and everything are all dependent on the relative stiffnesses of those elements. Now, if we look at more general structure, we can maybe describe the structural stiffness as being a series of simultaneous equations, and major part of the FE analysis is the solving of these simultaneous equations, and it generally does it by making them into a matrix form. Now, the actual solution of the matrix is not so important at this point. Well, it's very important if you're doing a PhD studying matrix solutions, or you're a developer, but from a user point of view, you just need to know there is a matrix going on in there, and the effects that this matrix can have, or the effects you can have on the matrix, and what it can do. For example, putting something of zero stiffness in there means you've got a line in there with zeros in, which means you're going to get divided by zero errors at some point. Likewise, a bar element has a limited degrees of freedom. So a beam will have 6 degrees of freedom, a bar will have 3. So a bar will contribute only 3 lines into the matrix, whereas a beam 6. So it's worthwhile honing the elements down for an efficient analysis. Also crucial to note is that as everything's derived from the nodal points, elements must share nodes to be connected. Point is occasionally forgotten. Now, releases. There's sometimes a confusion, I find, between restraints, constraints, and releases. Now, let's look at these and these. Some that sound a little bit similar, but not the same. Now, restraints, first of all the nodes in the model, in the FE model, are free to move, but their movement is controlled by the elements they're attached to, unless you add a restraint onto them in some way. So, typical restraint is foundation, support points, and so on. Then there's rigid constraints, maybe links, maybe joints, and these add an infinite stiffness between nodes, but without problems in the stiffness matrix, because it's not actually infinite stiffness, it's just making 2 points move together. If you were to add in a very high stiffness to the model, that would lead to mathematical problems in the matrix. Same way that if you have exceptionally small numbers as well. Typical use of this floor diaphragms, though there are other applications for it, such as maybe you're doing a stability model of just the cores, and you can link them together at floor levels with the rigid constraints. Third one is releases. Now, all elements in the model are fully fixed to their nodes, and hence to other elements, unless you add a release. Maybe you're doing a steel frame model, and you add in a moment release at the end of the beam, so as to model the steel connection. Interesting note, if you're interested, when GSA adds a release on the end of a member, what it's actually doing is adding an additional node in there, and then a joint between the two nodes together. So yeah, it's and if the release is a spring release, you have a spring stiffness, it actually puts a spring element in there. Likewise, if you put a spring restraint onto a node, it actually adds a spring element in there, all automatic. You don't have to worry about that. Another classic problem in FE models is the units. You think you're working in one unit, you actually find you're working in a different set of units. Remember Spinal Tap, when they got confused between inches and feet and got something quite different to what they were expecting. This comes in model size, this comes in loadings and properties and so on. If you think you're in millimeters and actually in meters, or vice versa, the end result will be completely different. One trick here is to maybe just switch on the section display in the model. Have a look. Does it look sensible or not? Related to that is the materials. Have you used the right materials in the model? Have you set the material properties correctly? I remember one example from a colleague of mine who was doing a footfall analysis, and footfall responses were coming way lower than we were expecting. We looked at the frequencies. The frequencies were coming out way lower than we were expecting. The reason was, rather than the 150mm concrete slab, we had a 150mm steel slab. Luckily, we knew approximately what we should be getting, and therefore we were able to spot that error quite quickly. And properties as well. I mentioned about zeros. You need to avoid properties, zeros in properties. For example, if you want to avoid bending moments in a beam, don't put the bending stiffness to 0. Use a bar instead. On the other hand, if you're doing a grillage model and you want to prevent torsion um, in the grillage, it's best not to put the torsional stiffness, the J value, to 0, but maybe put it something to very, very small. So there's minimum insignificant torsional stiffness, and therefore the bending stiffness takes over. Now the exception to this is shear stiffness, and zero shear stiffness in GSA switches off shear deflection. And let us look at that. Let me do an example for you. What I'm going to do is a model, and I'm going to do 2 multi-span beams. Put the nodes on, and pin those nodes, and I'm going to add loads onto those beams, and sections. I'm going to, let's say, something, and we're going to copy that down to there and make sure the properties of this second section, under modify for analysis, I'm going to set the K values, the shear stiffness values, to 0. And also, of course, make sure that those beams there are set to no shear. So when we analyze these, we then get bending moments and deflections, which look quite similar. And let's look at the values. So top beams with shear stiffness, bottom beams without shear stiffness, and you will note that the values are a little bit different. Both the so the lower ones, higher moment in the middle, lower deflection, and if you're doing hand calculations, the lower values, the lower ones will be the ones you'll be getting from your manual calculations. The upper ones are different, and that's because of the effect of shear deflection on those elements. Now, conversely, if I delete those results and change the loading from uniform to a point load in the middle, and then rather than a 0 shear stiffness, put in a very low stiffness and rerun this, we'll find that now that with a very low shear stiffness, the shear deflection is dominating on these elements, and that's also affecting the results. So watch out for that one. Location. Where exactly is the model in space? How far is it from the origin? The distance from the origin will make a big difference to the accuracy of results, and this is a classic problem if you're working on a BIM project. Now, FE analysis has a limited number of digits that it can play with for any particular number. I've exaggerated slightly here, and real ones have a few more, but take these two numbers. They look quite similar, but the decimal point is different. If this is a coordinate, the lower coordinate, being much larger, hasn't got the number of digits to the right decimal place left to actually give an accurate result. It's the further away you are from the origin, the lower the accuracy. You also might find the graphics are suffering as well. And this is a model we received a couple of weeks ago when the graphics were looking quite screwy down the left hand side there, and it was about 100,000 kilometers away from the origin. Move the model to the origin or close to the origin, and lo and behold, the graphics work well. So if you're getting a model which is looking strange like that, it's quite possibly the location in space. FE is not CAD. What I mean by this is that CAD and FE have different requirements. The purpose of a CAD model, whether it's Revit or MicroStation or AutoCAD or anything, the purpose of those is to represent the physical nature of the structure, its requirements, physical requirements, and communicate that to others, so the architects or the fabricators and so on. The FE model, on the other hand, is to mathematically predict the physical behavior of the structure and to help the design thereof. So the FE model is not there to look right, it is there to behave right. And that usually manifests itself in the question of element offsets. Let's go back to GSA. And again, I'm going to do a quick simple model, and I'm going to add in 2 beams, same length, pin those, add some loads, and same section on both. Doesn't really matter what it is. So we've got semi-supported beams here. Now by default, the beams are modelled, beam sections are modelled about the centroid of the section. Now this one here, let's add an offset on this one, so it's offset down to top of steel. So it now looks right. It looks more like the CAD model. Now what happens though when we analyze this? If we compare the bending moments, we'll see immediately that something is quite different. Likewise, deflections are lower, and also, interesting enough, there's now axial load on this element as well. Reason for this is the offsets have added in an artificial constraint on the element. If we switch on the reactions, we'll see that we are getting quite a large horizontal reaction on the ends of the beam. So this offset has turned this beam into a small portal frame. And if you put in offsets without really thinking about it, you can get some quite strange results, unexpected results. Floors expanding, contracting, or if they're resisting, that gap compact movement is resisted, then you get large forces forming. Now, on the other hand, this is what you want to do if you want to model a composite structure. So put the slabs in, the beams in, offset them appropriately, and you'll then get the in-plane forces in those elements as you would expect for a composite. So don't use offsets unless you need them. Loads. Yeah, you run the analysis and you don't get any results. What's the cause of that? So let's look at example received recently. Mention no names, but thanks Andy for this one. He had a grid load on his roof structure, but he wasn't getting any results out. We had a look at it, and grid plane number 4, he had restricted the element list down to just the main rafters, which can be very useful for grid loads to make sure that no additional elements get included in that by accident. But the problem was that element list excluded the elements parallel to the load span, which meant that no load panels were formed. Because of no load panels, the grid load had nothing to work on, and so we got no results out. Changed that element list to do something which included the horizontal members, and everything worked fine. Another cause of problems. You've defined loads, but there's no value in the loads. No load, no results. Conversely, you've defined an analysis case, but you've not included any load cases in the analysis case. I see this too often. Stability in the model. Models have to be stable. Now let's look at this steel frame model here. The beams have got pin ends. The column has got a pin support base. Problem is the columns themselves are torsionally unstable. There's nothing to stop those columns spinning about the axis. Fix for that, add in a ZZ restraint on the column base, which, let's face it, you've got 2 or 4 bolts down there on the column base. It's gonna give torsional restraint. Similarly, steel frame as a whole, the real steel frame will have a concrete floor in there, which acts as a diaphragm. The model without that is it's maybe stable around the brace bays, but elsewhere from that, it's a bit wobbly. You need a rigid constraint on each floor level to make the structure work, and of course get the loads to the braces. We'll come back to this in a bit. Convergence. Now, there are a number of analysis options in GSA which are iterative, particularly the non-linear, static non-linear, and the raft analysis. And sometimes you need to help GSA find the answers. Now, we do this by means of damping. Damping restricts how the solutions are bouncing around a bit, and generally, especially non-linear, there's an automatic damping that happens, which usually works well, but sometimes you'll find for some reason it's not, and you might need to go and give it a hand. So you might say, well, change the viscous damping to an artificial damping. That sometimes works. I find artificial damping is usually slower to converge, but can be more reliable sometimes. Likewise, the automatic adjustment of the damping, if that's not working, you might need to go in and force a constant damping, set it off at 50% to begin with, reduce or increase that accordingly to see, which is giving convergence the quickest. Likewise, what you're converging to. The default might be quite a fine result, and especially on raft analysis, you may find that there comes a point where GSA just does not want to converge any further. It just reaches the plateau and stops there. Now, if that's 1 millimeter difference, 0.1 millimeter difference between the soil and structure, that's probably close enough. If it's 100 mil difference between the two, it's not. So there is the option to move the goalposts during the analysis. These images there are showing in the setup, but you do have the option during analysis to actually go in and change those as you go through. And obviously, if you change the residuals, the goalpost, to something too large, your results will be low accuracy. It's the art of engineering, knowing when the answers are close enough. Sizes of the models. Basic concept: large scale models for overall behavior, detailed models for local behavior. For example, the connection on the left. You might model this connection in 2D elements and springs underneath the base plate and around the holding down bolts and so on. And that's very appropriate for such a detailed model, but you would not want to do that with the large model on the right hand side. That would be nonsensical. Right model right, you just put a pin restraint or a fixed restraint on the bottom of the columns. Decide what you want out of the model and build that model accordingly. And if you need several models, build several models. Don't believe that you can do everything in the one model. You can do everything in the one model, but it's not normally advisable. You'll probably regret it. Meshing 2D elements. Shape and size and so on is important to the mesh. Now, let's look at this flat slab example. 4 images on the right, gradually increasing the mesh density. And you can see the top left with the crudest mesh, we're getting quite large gaps in the contours. It's insufficiently fine. We increase the mesh density, we're getting better contours. But you also note the moment in the middle over the support is also increasing. And this is a mathematical anomaly for in FE. You've got two-dimensional slab shell elements, and they are two-dimensional. They just have width and length, supported on a one-dimensional column. It's just a point. The finer the mesh, the higher that peak moment will get in the analysis. Thing to remember is this is an area where FE diverges from reality. Reality is columns have dimensions, slabs have a thickness, and the moment will be occurring not over a mathematical point, but over the interface between the column and the slab. So whether you sort of just say, here the mesh is fine enough. I mean, this mesh in the bottom left is probably sufficiently fine. The contours are pretty smooth, not perfectly, but and likewise the peak moments within the column area I can probably ignore. So it's worthwhile increasing the mesh density, but remember that in certain circumstances it can lead to strange results. Here's another example. This is a buckling analysis, and covered in more detail in one of the blogs on the website. And similarly, it's looking at buckling of a hyperbolic cooling tower. Mesh density on the left, low. Mesh density on the right is high. And when you compare the results of the buckling load factor as you increase the mesh density, you can see there's quite a correlation. Very low mesh density, the results are very unreliable. Increase the mesh density means you're getting a much better result, and you can see also the difference between the linear and the parabolic elements are coming together. And you can see when we get to 5 degrees to 2.5 degrees, there's not much improvement between the two models. So probably 5 degrees in this case is probably a sufficiently fine mesh. So, apart from things where to look, what are some other tricks and tools that you get in GSA? First thing, always do, look at the deflected shape. Does the deflected shape look right? If you're doing a static analysis, run a dynamic one as well. A typical building floor should be vibrating between 4 and 10 hertz. Bridges maybe between half to 5 hertz, those sort of ballpark figures. And if your frequencies are coming in those sort of ranges, then that's a good sign. If they're outside those ranges, something to look at. Likewise, if you're doing a dynamic analysis, run a static one as well. And looking at the model in a slightly different approach can indicate problems, and can help you solve things quite quickly. Likewise, if something is just not right, maybe you're getting singularity errors, or the condition number is high. And by high we mean, well, over e to the plus 10 is getting a bit wobbly. Over e to the plus 15, you've got a mechanism and you need to deal with that. GSA now has a model stability analysis. In fact, it's had in there from 8.6 as well, and this can be very useful for finding out where the problems are in the model. By way of example, let me do another GSA model for you. What I'm going to do is I'm going to quickly throw together the steel frame that we saw earlier. Let's say bays, and I'm going to add in columns, beams. I'm going to pick a suitable size and just for simplicity copy that over. And here is our steel frame. Now let's add in some supports. And pin those. And I'm also going to add moment releases on the ends of the elements. Now, I use the find option and find the property beam 2, property beam 3, property beam 1 as the columns, and modify those so that the beam releases release the rotations, but I will fix back again the torsion, the XX release. And we can see that everything's there. Now, we also want intermediate beams. So let's go for a plan view, and let's pick these ones now as a 6 meter span. Let me copy those over. 2 copies, 2 meters. That's good. Now at the moment, these beams at the end are not actually connected. These secondaries are not connected to the primaries. And we can sometimes find these by calling up the graphic wizard, double click on it, and say highlight edges. And we're getting end marks, which we do not want. So let me select all those. I'm going to join everything up with the sculpt command, connect 1D elements. So whenever 2 elements cross or touch, they will add in, break the elements and add in node points. Right, let's just clear that highlight edges off the node. Now, being a steel frame, we also need some bracing. So I've got defaults, and I'm going to cheat and just use the column section by setting these bars. Add those in, making sure I'm clicking to the nose, not the elements. And just rotate around and add them in there as well. Okay, So we've got our model, and just simplicity, we're going to add in some dead loads, well, self-weight, and let's analyze this and see what happens. And we are getting a very high condition number. Not good. Interesting enough, if I hadn't added the braces in, I would have had a matrix singularity. So let's use the model stability analysis. I'm just going to ask for 10 modes. Note we've got low stiffness modes that we're looking for. Can also find high stiffness modes. It's a new feature in 8.7 to find very high stiffness elements. And it's found a number of modes. So let's look at the shapes of these. Now, it's not showing any deflection, so let's call up our displacements, set it to actual values, no displacements, rotations in the hands. Okay, we're gaining rotations, and let's show them on the beams, a little bit easier to see. Nope. And we can see we're getting rotations on the columns are torsionally unstable. So let's fix that. Go in and add ZZ restraints on those columns and rerun the analysis. And this time we're getting a much better condition number, +8. That's pretty good. I like that. But what's the stability analysis showing us now? We're now getting, it's showing up racking of elements. Let's go to plan view. Oh, let's change that to no displacement, maybe touch easy to see now. And we are getting a number of racking problems. And in fact, if I change the gravity load to include just 1% for a bit of notional, and then analyze the static load, you can see that up to maximum, we can see the deflections are excessive. We need the diaphragm. So let's raise those results. And to set up the diaphragm, the quickest way to do it is to select all the nodes on a floor, and there is, under the sculpt menu, option to create rigid constraints. Let's do the same on that one. Use the repeat command. Now we can't see these yet, so let's switch on the display rigid constraints. So you can see the rigid constraints there. Now the rigid constraints will by default be fully restrained, which is no good because we want different vertical deflections. So I just restrain them in the XY plane. And if you run the static analysis now, we should see that we're now getting much more sensible results, including, I can't see those now, including bending moments and so on. Actually, also to note, we're seeing sagging on the braces, and I'll just go and just switch those off to exclude the intermediate results on the bars. So a nice stable model with the results we can now work with. Some conclusion. Mistakes are easy to make, so be careful. Think about what you want to do in the model. Think about what you are doing in the model, and think about the results when you get to the end. Are they what you expect? So summary, things to look when things not right. Check your units, check your materials, check your properties, check your loads, check your connections, and check your locations. And use the analysis options to help track down the problem areas. So I've shared some of things I found. If you have any questions you want to ask, or whether or any examples that you want to share, do feel free to type them in.